Our project is based on the use of sweep frequency capacitive sensing technology, which is capable of identifying various signals produced when touching an object, and thus detecting the touch patterns to define the contact gestures on the object, and then to be able to configure gestures and tasks that correspond for each actions. Applying that to common objects as control module in order to interact with various electronic devices.
Hello, my name is Bruno Vergara and I am going to introduce you to our project. Well, we started making a lot of ideas of what we could do to project. Finally, in our research, we found the sweep frequency capacitor sensing. When we see that, we know that will be a lot of work, but that is so useful, you know. The sweep frequency capacitor sensing is something that it's unreplaced, and you can do a lot of things with this, with only your hand, your fingers, or every movement. You can make a control your TV, your computer, your smartphone. You can make a lot of tasks with this. Okay, and our objectives. Well, we have objectives general and particulars. Our general was to implement our sweep frequency capacitor sensor technology to adapt objects to different device controllers. Okay, and more particularly, we can build a system for movements that perform a specific number of actions, implement a prototype that gives the user full control over the actions to be performed, provide comfortable or efficient system for the user, and give the ability to customize the gestures or actions performed. What I mean with that? Well, we can see that with my partners.
Hello, my name is Jimenez Gomez Andres, and I'm going to be talking about the different stages that we are going to take in order to finish the prototype of the project that we are currently working on. It is important to mention that this is the planification of the things that we are going to do during the next year. So there are some things that might be subject to change depending on the problematics that we could have during the next year. So with this information set, let's start with the first part of the development of the project. There is going to be the investigation part, which is the current stage that we are working on. Now, in this stage, we are looking for information about electronic components and circuit designs that could help us in the elaboration of the prototype, of the physical prototype. Now, this is only theoretical information that is gonna help us to have like a preview of the things that we are going to confront in the future when we are like building the physical circuit. When we were making the planification of the project, we noticed that there are two topics that are going to be essential for the project, for the prototype. And basically, these two topics are the generation of signals and the manipulation of signals. And keep in mind these two topics because they are going to really be important in the outcome of the project. I will talk more about them in a minute, but keep this in mind. So, when we have all the information that we need in order to start working with the initial part of the prototype, we are going to start with the second stage, that it is the experimental part. In this part, we are going to make some experiments with the circuits previously designed. So we are going to build them up and we are going to check the results, if they are working well, if they are not working, if we can make some improvements to the circuits, etc. If we get positive results, we are going to start building the initial part of the product. If no, we are going to make an evaluation, and we are going to change the logistic of work that we have been doing for that time. Now, when we finish the first part of the prototype, the physical part, we are going to pass to the third stage. There is a manipulation of signals. So, in this stage, the analogic signal that we get from the first part of the circuit, we are going to convert it into a digital signal. Because if we convert the analogic information to digital information, we can work with that information. And that is going to be really helpful when we want to apply that information, but more on that in a minute. Now, we are going to make this with the help of an ADC circuit. It is going to basically convert, as I former mentioned, an analogic signal to a digital one. And this is going to make the difference between a binary system and a multiplexing system. Now, a binary system is only going to tell you if you are touching an object or not. A multiplexing system is going to tell you if it's not only going to tell you if you're touching an object, it's going to tell you how you're touching an object. So the position of your hand really matters in this type of system, because it's going to give you different information from the signal that you are receiving. Now, when we finish the ADC circuit and we can see that we are receiving information by the signal generator, we are going to start with the application part. Now, this is the part where we are going to discuss where do we want to apply the circuit, because the applications that we can take for the circuit are a lot. So the main idea is to put it like a system in a house, to make a semi-automatic house with the help of like a stool that, depending on the way you touch it, you can control different parts of the house, or electronic devices, or the locks of the doors or windows. There is just like the primary part, but we haven't decided yet what we are going to apply it. This is going to be all for the four stages that we are going to follow to complete the prototype and almost finish the project.
The materials that we are going to use are Arduino Mega. It have 54 digital pins that can work as an input-output, 16 analog inputs, a 16 MHz crystal oscillator, a USB connection, a reset button, and an input for powering the board. The communication between the computer and Arduino occurs through the serial port. It has a USB serial converter, so you only need to connect the device to the computer using a USB cable. Arduino Mega can be powered through the USB port with an external power source. The fitting is selected automatically. When working with an external power source, an AC-DC converter must be used, and his voltage must be regulated within the operating range of the board. In the same way, the micro can be powered by using batteries. Preferably, the voltage should be in the range of 7 to 12 volts. The Arduino Mega has some pins for powering the circuit apart from the power adapter. Voltage input through this pin is possible to supply the power to the board 5 volts. We can obtain a voltage of 5 volts and a current of 40 milliamperes from this pin. 3.3 volts, we can get a voltage of 3.3 volts and a current of 15 milliamperes from his pin. GND, the ground, 0 volts of the board. Then we have the capacitive sensing library. For the development of the project, we opted to use an Arduino Mega, in which case we will use a library to detect the variability in a capacitance of the circuit. When it comes into contact with the human body, the Rhino's capacitive sensing library converts two or more pins of the device itself into a detectors of the capacitance of the human body. Resistance. A resistor is an electronic component considered as a passive basic component. It consists of two terminals and has no polarity. Its main function is heat dissipation, a process in which electrical energy is converted into a thermal energy. Capacitor. It is a passive component like resistors, but they have the characteristic of storing energy in the way of an electric field. This field is the result of the separation of the electric charge. It is formed by a pair of conductive surfaces generated of sheets or plates which are separated by the dielectric the material or a vacuum. The place subject to a potential differential acquire a certain electrical charge. The variation in total charge being zero. A capacitor is a two-terminal device and can have polarity at its terminals. Inductor. Inductors are passive elements like resistors and capacitors, but they have the characteristic of storing energy in the form of magnetic field. The simplest form of inductor is a coil of wire that has a tendency to maintain its magnetic field once established. Inductor sensor. A coil detects the passage of a ferromagnetic element in its vicinity, and generating an electrical voltage at its end. 1N4148 diode it's an fast electronic component made of silicon with high conductivity, used in the processing and detection of the radio frequency signal very efficiently, with a reverse recovery time no more than 4 nanoseconds.
Hello, my name is Baltasar Rubio Rafael and I will talk about the story of the touchscreen. This story involves many companies and schools. The story of the touchscreen starts in 1965 when Eric Johnson, a member of the Royal Radar Establishment, Johnson wrote a short article about his work in capacitive touchscreen. This article was expanded upon in 1967 and a year later an application of touch technology in service of the air traffic control was described in an article. Subsequently, in 1967, Frank Beck and Ben Stupe, both engineers for the European Organization for Nuclear Research (CERN), developed a transparent touchscreen which was based on Ben Stupe's previous work in a TV factory in the 1960s. It was later manufactured by CERN and launched in 1973. In 1971, Hello Graphics, founded by American physicist George Somerhalder, developed a patent for a version of resistive touchscreen technology. In 1977, Hello Graphics partnered with Siemens for the development and transparent implementation of opaque touch panel technology developed by Somerhalder. The resulting technology was shown off in 1982. Meanwhile, in 1972, members of the University of Illinois applied for the optical touchscreen patent, which subsequently became an essential part of the Magnavox Play 2 student terminal that had on the display a cross matrix of 60 by 60 infrared sensor consisting of a LED on each of the screens and phototransistor on the other edge. This way, any opaque object the size of the fingertip that was near the screen could be detected. Later in 1983, HP 155 was released, which was one of the first commercial computers to have a touch screen. These displays also implement infrared transmitters and receivers around the frame of each sonic cathode ray tube that also detect the position of a non-transparent object on the screen. In 1984, Fujitsu developed and released a touchpad for Fujitsu's Micro 660, which aimed to adapt to the complexity of kanji characters, the latter stored as mosaic graphics. In 1985, Sega launched the Sega Graphic Board, and as a accessory of the SG-1000 video game console and SC-3000 computer. It was a pencil and a plastic slate that later had a transparent window that detected the pressures the pencil made on it. And a year later, a graphics table was released for the Sega AI computer. Meanwhile, in 1982, multi-touch technology began to be deployed, which would be evolution of the technology. Multi-touch technology began in 1982 when the University of Toronto developed the first multi-touch human entry system using a frosted glass panel with a camera placed behind the glass. Later, in 1983, Bell Labs published an exhaustive discussion of touchscreen-based interfaces. A year later, the Bell Labs company and Carnegie Mellon University (CMU) already had prototypes of the working multi-touch displays, and both input and graphics could respond interactive to multiple fingers inputs. The Bell Labs system was based on capacitive fingers coupling, and the CMU system was optical. In 1985, a demonstration was made of the multi-touch gesture of zooming when pitching the screen, and the SMU system. There's advanced were dedicated to developing phones with multi-touch screens. In 1993, IBM launched the IBM Simon cell phone, which was the first touchscreen mobile phone. Much later, in May 2007, LG product was released. It was the first phone with capacitive touchscreen before the launch of the first iPhone. The last tactile technology was implemented in the 2055 Apple Watch, which is sensitive to the force with which is touched.
At this point of the video, we already heard the capacitor sensor or swift capacitor sensor or something, and I'm going to explain you what is capacitor sensor. Well, capacitor sensors are sensors capable of distinguishing the potential difference between a person's electrically polarized finger members. What does that mean? The sensor can disguise between metal and not metal items, and with their sensitivity can be modified depending the object to be detected. Our human body are electrically charged, and with that, the capacitor sensor can make a signal or make something works, some action to make. That's the first, the everything, the base of our project. The capacitor sensor is the most important thing on our project. In the human body, the electrical charge, our fingers, our arms, or any movement can make the signal disturb, and that disturb is an action. And the other kind of disturb is another action, and in that way we can make a lot of actions with a lot of movements, a lot of fingers, a lot of commands. We can name that in that way, and that technology can open or mind to a lot of solutions of a lot of problems.
Hello, my name is Marta Olvera Omar Stankiewicz, Team 3, and I will tell you about multi-touch technology. What is multi-touch technology? Multi-touch technology has been working with trackpads or touchpads and touchscreen interfaces, such as those found in laptops, smartphones, and tablets. It allows users to interact with their devices in multiple ways, expanding the number of interface options rather than use swipe and tap. Multi-touch lets you zoom, pan, select, and move. It's designed to provide touchscreen interfaces with the same kind of flexibility and ease to use provided by a traditional mouse and keyboard, while providing a more intuitive and seamless user experience. Multi-touch examples. Examples of multi-touch technology in a practice includes smartphones, tablets, touchpads, and walls, such as those has been found in a museum exhibits and a commercial space, and laptops with trackpads. All of these devices allow individuals to interact with them in different ways. Thanks to multi-touch technology, for example, you can zoom in or out by applying or spreading two fingers through a touchscreen or trackpad. This is the nature of multi-touch technology. Different hand gestures lead to different functions. How does multi-touch work? Multi-touch technology works with touchscreen and trackpad interfaces. Both surfaces are capable of measuring and responding to pressure through the use of a pressure-sensitive panel that carries an electrical charge. When pressure is applied, the electrical charge is interrupted, which is read by the computer as an input. The device software then translates this input into a corresponding movement or function. Multi-touch technology allows these panels to read and interpret multiple pressure points, including gestures, at the same time. Touchscreen can be capacitive, as many modern mobile phones are equipped with and are operate only with the fingers. They can also be made of an array of optical sensors. The most important characteristic is that it allows obtaining the position of several points of contact on it. Simultaneously, it also often allows you to calculate the pressure or an angle of each the contact points independently, allowing you gesturing and interact with multiple fingers or hands simultaneously, similar to mouse cuts, and thus provide of a better interaction through much more intuitive gestures. The future of multi-touch. As touchscreen interfaces has become more common, we can expect more and more users of this technology to be made. Multi-touch technology already allows users to slide, scroll, select, zoom in, zoom out, and move the cursor. In the future, you will be able to manipulate objects that were once static and 2D in a 3D realm. You can rotate objects, flip them, or manipulate them in other ways through a simple hand gesture.
Hello, my name is Nicasio Sanchez Natalia, and I'm going to talk about signal processing. In industrial monitoring, sensors record environmental factors. Within the processes, sensor signals reorder continuous change in the monitoring file. One usually works with digital and analog signals. An electrical voltage or current value is typically generated, so that is proportional to the physical magnitudes you want to control. In cases where autonomous processes must maintain constants or reach certain states, analog processing of signal is required. Analog signal processing is especially important in automatization. Standard electrical signal magnitudes are common in signal processing techniques. One of the many ways for obtaining a digital value from analog signal is to use an AC-DC circuit, for which the following steps are required. Step number 1. Signal sampling. To convert an analog signal to a digital signal, the first step is to sample it. The same, which is to say, take different voltage samples at a different point of the sine wave. The frequency at which sampling is performed is called resonant rate or simple rate and is measured in kilohertz. In the cases of a digital audio recording, there are more samples taken. The higher the quality and fidelity the resulting digital signal will have. During the sampling process, numerical values equivalent to the existing voltage or voltage are assigned at the different points of the sinusoid, in order to then perform the quantization process. Step number 2. Quantization of the signal. After sampling, the next step is the quantization of the analog signal. For this part of the process, the continuous value of the sinusoid are converted into discrete decimal numeric value series corresponding to the different voltage levels of the variations contained in the original analog signal. Therefore, quantization represents the sampling components of variation in the stress value or voltage taken at the different points of the sine wave, which allows them to be measured and assigning their corresponding values in the decimal numerical system, before converting those values into a binary numerical system. Step number 3. Encoding the signal to a binary code. After quantization, the values of the voltage outlets are represented numerically by pre-established codes and standards. The most common is to encode the digital signal into a binary numerical code. Applied to the project, it is intended to sample the signal emitted by the touch patterns. Then, this signal will be analyzed in order to obtain the highest peaks of each touch pattern. After that, with the Fourier transform, we will be able to obtain a more defined wave. With the value of the peaks, a table will be created to have an ID for each of the touch patterns provided by the user. An example of the work planning to be done is the experiment previously conducted by Colin Hickman, which is cultivating frequencies. It's a hydroponic garden and sound installation that uses this technique for SFCS and the sweeping cap sense library to turn each of the 15 plants into touch sensors. The installation also includes several hydroponic sensors to collect data and use it to drive a generative system music. The touch-sensitive plants encourage users to interact with the garden as a living thing and a sound installation. Musically, the plant sensors give the users note level and effect level control over a series of oscillators and audio effects. Max MSP was used for the sound design and generative system, and Arduino Mega, with a custom designed and printed shield, was used for the touch sensor and ultrasonic sensors.
Well, when we started making ideas of our project, we had a problem. We started making it on Arduino, and we had to translate that to assembly language because we have to use everything of our subjects. The subject of microcontrollers are microprocessors. Actually, this was so annoying. The assembly language is so complicated, and we started our research about how we could implement this technology into a assembly language with the PIC 18F14K15. That's the serial number of the PIC. And we are already in that research making a lot of ideas of how we could implement that thing. And that's it.